Keeper 4.1, Introduction to Power Series. All right, so let's do a little recall of our geometric series. We know that if we're given a geometric series of a times r to the n, we know that equals a over 1 minus r. Given that, or provided that r, or the absolute value of r, is less than 1. So if this is true, and we let a equal 1 and r equal x, then the same fact holds true. So the sum as n goes from 0 to infinity of x of n would be equal to 1 over 1 minus x, given that, or provided that, the absolute value of x is less than 1, just like it was true for absolute value of r being less than 1. All right, so we can write this backwards. If I'm actually given the function of 1 over 1 minus x, that's going to equal the sum from 0 to infinity of x to the n, again, where x is, or absolute value of x is less than 1. All right, so this fact that we see here is actually something that you need to memorize. You need to memorize that 1 over 1 minus x is the sum from n equals 0 to infinity of x to the n. You guys need to know that. All right, so here's an example of how we can use that. So it says find the power series representation for the function and determine the interval of convergence. And so they're giving us a function g of x equals 1 over 1 plus x cubed. Now, what you want to try to do is rewrite this function to look like our known function of 1 over 1 minus x. So the very first thing I'm going to do is I'm going to rewrite the function. And instead of 1 over 1 plus x cubed, I'm going to rewrite that as 1 over 1 minus negative x cubed. So what I end up having is a number over 1 minus another number. All right, so now that I have it rewritten, I can build that series that I just rewrote, starting with what we know to be true. What we know to be true is 1 over 1 minus x is equal to the sum from n equals 0 to infinity of x to the n. And I actually wrote out some of the terms of the series just so you guys can see like how I'm building it up. All right, so now that I have my known, I'm going to go and again try to build my series g of x. And so I'm going to start by changing the x to be negative x cubed. And so instead of 1 over 1 minus x, I'm going to write that as 1 over 1 minus negative x cubed. In other words, everywhere I see an x in my series, I'm going to replace it with negative x cubed. So I'm going to end up with 1 plus negative x cubed squared plus negative x cubed cubed, and so on, all the way till I get the sum from n equals 0 to infinity of negative x cubed to the n. All right, so at this point, technically I've built my series, and technically I'm done, but because we like to write our power series so that every base has its own individual power, I would probably rewrite this summation to be negative 1 to the n times x to the 3n. Now, if we want to find our interval of convergence, remember x has to be between negative 1 and 1 for this to work. Well, in this case, our x, or our base of our exponential, is x cubed. So I want x cubed to be between negative 1 and 1, which means our interval of convergence is that x has to be between negative 1 and 1 when I cube root both sides. All right, so example 2, we're going to do the same thing. Again, I'm going to rewrite this function to be 2x squared, or something over 1 minus something else, and in this case it's negative x cubed. And then again, I'm going to build my series starting with my known. So I'm going to start with 1 over 1 minus x, which is the sum from n equals 0 to infinity of x to the n. Then I'm going to change that x to be negative x cubed. So everywhere I see a x, I'm going to put negative x cubed. And so that gives me the sum from the previous example. This one's a little bit different though because they have the 2x squared on top. So what I need to do now to continue building my series is to multiply it by 2x squared. And so every term of the series, I'm going to multiply by 2x squared, giving me a sum as n goes from 0 to infinity of negative x cubed to the n times 2x squared. Now again, I could technically leave my answer like that, but it's not like the proper form for like a power series. So I'm going to rewrite it so that everything has its own, every base has its own exponent. And so I have negative x cubed to the n times 2x squared, or 2 times negative 1 to the n, x to the 3n plus 2. All right, now again, just like before, We know that whatever that base is of the exponential has to be between -1 and 1. Again, this base was just x cubed, so if I cube root both sides, I still get an interval of convergence of -1 to 1. All right, example 3, it says find the power series for f of x equals x over 5 minus x. Again, just like before, I'm going to rewrite my series. Now, in order to do this, again, I need to have a number over 1 minus another number. So I have to get rid of that 5. And so when I rewrite it, I'm going to pull out the 5. And so I'll be left with x over 5 times 1 over 1 minus x over 5. All right. And again, the whole point of that is you want something divided by 1 minus something else. So I had to factor out 5 in my denominator. All right, so again, I'm going to build my series. I'm starting with my known. So 1 over 1 minus x is the sum from n equals 0 to infinity of x to the n. I'm going to change that x to be x over 5 to try to build my series. So everywhere I see an x, I'm putting in x over 5. Then I'm going to multiply the whole thing by x over 5. And so every term that I have in my series, I'm going to multiply by x over 5. And so I'm left with the sum of, as n goes from 0 to infinity, of x over 5 to the n times x over 5. And again, just to rewrite it properly as a power series, I'm going to write each base to have its own exponent. So I'm going to have the sum as n goes from 0 to infinity of x to the n plus 5 over, or sorry, x to the n plus 1 over 5 to the n plus 1. Now, here we have a different base of our exponent. It's not just x to some power. This time, the base of our exponential function is x over 5. So I have that x over 5 has to be between -1 and 1, or my interval of convergence would be, if I multiply both sides by 5, -5 to 5. All right, so we can also take derivatives and integrals of power series. And you take your derivatives and integrals just the way you would if it was a regular function. Nothing special, nothing new. The new thing is, though, that whatever radius or interval your original function had before you integrated or before you took the derivative, your new function or your derivative function or your integral function will also have that same radius and interval of convergence. All right, so it says find the power series representation for the function 1 over 1 minus x squared. The first thing you need to do is recall that 1 over 1 minus x squared is the same thing as the derivative of 1 over 1 minus x. Again, everything we do, we're trying to get back to that 1 over 1 minus x. And so if you recognize that that's the derivative, well, you could just build your series. So you start with your known of 1 over 1 minus x. And then we're going to take the derivative of it because I know the derivative of that equals my function that I need. So the derivative of 1 over 1 minus x, and again, I'm showing it term by term so that you guys can see where I'm getting my pieces. So like the derivative of 1 is 0, the derivative of x squared is 2x, the derivative of x cubed is 3x squared, and so on, all the way until the derivative of x to the n, which is nx to the n minus 1. And so I have the sum as n goes from 1 to infinity instead of 0 because my first term goes away. So I have to move my step up a little bit. So instead of starting at 0, I'm starting at n equals 1 to infinity of n to the x, or n times x to the n minus 1. All right, so that tells me that my original function, or the function I was looking to build, of 1 over 1 minus x squared is simply the sum as n goes from 1 to infinity of n times x to the n minus 1. Now, the interval of convergence of our known series, or what we started with, or what we took the derivative of, the interval was from -1 to 1, so that means it has a radius of 1. And so that means that the derivative function also has an interval from -1 to 1 with a radius of 1. All right, so example 5, it says find the power series for the function and determine the radius of convergence. This time our function is h of x equals ln of 5 minus x. Again, your whole goal is to make this look like 1 over 1 minus x so we can use that to build a series. So if you recall, we have the integral of 1 over 5 minus x is the same thing as negative ln 5 minus x. So if I integrate 1 over 5 minus x, I could basically get my series that I'm looking for. I just need to negate it to get rid of the negative sign. All right, so I'm going to start with my known. I'm going to start building this series. So I start with the 1 over 1 minus x. We know that's the sum as n goes from 0 to infinity of x to the n. This time I'm not going to show every single term, but you can. You can show every single term if you need to. All right, so instead of x, I'm going to change it to x over 5 because in the original function or the original integral that I'm trying to eventually get to, I need to factor out the 5 to make it 1 minus something. So I'm going to change my x to x over 5. And so I have the sum as n goes from 0 to infinity of x over 5 to the n. And then I'm going to multiply it times the 1/5 to account for that 5 that I factored out in my denominator. And so I have the sum as n goes from 0 to infinity of x over 5 to the n times 1/5. And then I rewrite that so that each base has its own exponent. So I know that 1 over 5 minus x is simply the sum as n goes from 0 to infinity of x to the n over 5 to the n plus 1. Now remember, we know that we need to integrate this in order to change this to like an ln function. So we're going to integrate 1 over 5 minus x dx. And when we integrate that, remember you add 1 to your exponent and divide by your new exponent. So we're going to have the sum as n goes from 0 to infinity of x to the n plus 1 over n plus 1 times 5 to the n plus 1 plus some constant c. All right, so let's continue. So again, there's my function. Now I need to figure out what the c is. And so, well, before I find the c, I'm going to go ahead and negate it to get my actual function. Remember, the integral was negative ln 5 minus x. But if I want ln of 5 minus x, I need to take the negative integral. So that's going to give me c minus the sum from n equals 0 to infinity of x to the n plus 1 over n plus 1 5 times, or 5 to the n plus 1. And now again, I need to find my c. So to find c, I'm just going to plug in some value for x and see what it gives me. Now in this case, and in most cases, you can plug in x equals 0, because when you plug in x equals 0, it's going to give you a nice summation. And so I know that I have ln of 5 minus 0 equals c minus the sum from n equals 0 to infinity of 0 to the n plus 1 over n plus 1, 5 to the n plus 1. And so that summation actually comes out to be 0 because 0 in my numerator would cancel out everything else. And so I have ln of 5 equals c. Now plugging that c back into my function, I know that the ln of 5 minus x equals ln 5 minus my summation from n equals 0 to infinity of my new function. All right, now since the radius of the original function of the 1 over 5 minus x, since that radius is 5, the radius of my integral function is also going to be 5.